The following program is brought to you by Element14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Hello and welcome back to Element14 Presents. My name's Caleb. In today's episode, we're going to build a configurable NTP synced world clock.
Amazing hacks. Inspired designs. Each week, Element14 Presents brings you innovative projects using electronics, engineering, and more.
All right, here's the problem I'm trying to solve. Depending on what I'm doing, I work with people in many different time zones almost every day, and I want to be able to see at a glance what time it is in their time zone. Part of it's my own curiosity, and part of it's because I don't want to be late for meetings, so it is valuable for me to have this information at a glance. And yeah, I know that there's a million options out there for world clocks. There's commercially available options, there's one on my phone, there's one on my computer, and there's probably billions of them on the internet that I could just pull up in a web browser and view. But I'm sticking to my theme of having more buttons and knobs and switches and displays all around me. It's kind of like Adam Savage's first order of retrievability, but with information instead of tools. Instead of having to dig in my pocket, pull out my phone, unlock it, hunt down the right app, open it, and view information, I can just glance down and have the information that I need. So here's the idea. A device that's on all the time that has multiple time zone displays. Each time zone will have a clock, a title of the time zone, and an offset in hours from my current time zone, and the ability to configure each one of these to set to different time zones as I need them. And to do that, I'll use a rotary encoder and have to build some software menuing system so I can cycle through each one of them and set options. Instead of using a real-time clock, I wanted to use Network Time Protocol, which is NTP for short, and it's a service that's on the internet that you can pull a very accurate time off of whenever you need. So I'll never have to set this clock, and if there's any drift in the system due to the Arduino being fast or slow, or more likely bugs in my code, it can just sync periodically and reset itself, and the time will always be accurate on this thing. So now that we have an idea of what the goals are for this project, let's have a look at the parts so we can get started. I selected the Arduino Nano IoT33 for this project because it's got Wi-Fi for NTP, it's small, and I really enjoyed working with it last time, so I'm going to use it again. The main display for this project is the 3.5-inch Adafruit Pi TFT. Why the Pi TFT? Well, I had one in stock and it was easy to test with. Even though it's designed to run on a Raspberry Pi, it runs on SPI, and there are libraries for the Arduino that allow it to run. It doesn't refresh all that fast, but if you write the code just right, it doesn't really matter. For the encoder, I'm going to use the same good old Bourne's encoder that I've used in a bunch of other projects. It's got a great feel, I know what libraries to use, and it's super easy to connect to an Arduino. I found these 4-digit 7-segment displays that have dots between the two centered digits on the display, which is perfect since we're going to be displaying time. They are common cathode and made by a company called Vishay. They're going to take a bunch of I/O pins, so I'll probably use a couple of MCP 23017s to drive them. Awesome, we've got an idea, we've got all the parts, let's get it out onto a breadboard and get through some design and start building this thing. And here's the breadboard all done. I didn't film it because this is the second or third iteration of the configuration on this project, and it just got to be a mess. I'll go through and I'll talk about how it's wired up and how a few of the components work. Got the MCU, the Arduino Nano IoT33, got the Adafruit Pi TFT. With some help from DJ, I was able to get this thing running because it just runs on SPI. I didn't realize that, but it is. It's just SPI. So I've got that wired into the hardware SPI port on the MCU. The next thing is the rotary encoder. The 2 pins on the bottom are the push button. So one's going to ground, another one's going to GPIO. The 3 on the top, the center pin goes to ground, and then 2 more to interrupt GPIO pins on the Arduino. The 4-digit 7-segment displays are the part that gave me most of my problems. And it's because I didn't know what the right tools were to use for that. My go-to, my first thought was Okay, it takes a bunch of pins. I don't have that many on there, so I'll grab GPIO expander. And what I reached for initially was the MCP 23017, which I've used quite a bit, familiar with it, and they usually work great. But it didn't work great for these, and I'll explain that, but we got to go backwards and talk about how these work a little bit. And I'm going to plug it in so it's easier to explain. The sketch that's on here is very basic, and it's just showing hello world here and some numbers on that, and the clockwise, counterclockwise, and button push go out to the serial console in the Arduino IDE, which isn't even on right now. These specific displays are common cathode 4-digit 7-segment displays. And in this case, what that means is there's a digit pin, which is the common cathode for all of these LEDs. And then there's another pin for each one of the LEDs, which is the anode. And these are labeled A, B, C, D, E, F, and G. And that works. You just pull this low, pull this high, and it'll light up that LED. The problem is that if you pull all of these low and whichever ones of these high that you need, since there's an 8 in here, every one of these digits is going to be an 8. And the way that I understand that this works is it's all about the refresh, and it's turning the LEDs on and off so fast and in a way that you can see these and you can't see these segments. So when I had that hooked up through the MCP, it just wasn't fast enough because the library that I was using, which didn't support the MCP, and then I wedged it in there, and there's a good reason why it didn't support the MCP, is because that it had to digital write every pin to turn it on, and that took one cycle of the Arduino for each one of these. I ended up talking to some of the folks on the Adafruit Discord channel because I was using the Adafruit library for this, and they pointed me to a function that would write all 16 pins all at once. So that sped it up significantly, and that totally worked, and I was happy with it. And then I moved on to work on this portion a little bit, and what I found was when this writes, it's blocking. It just stops the Arduino completely until it's done scanning through, and the Arduino picks up again. I checked in with the Adafruit people, and there's, without significant changes or completely rewriting the library, it's unavoidable. It is blocking. There wasn't a way around it. At least that's what they told me. In that same conversation, somebody piped in and said, why don't you just use the right IC in the first place? Well, my answer to that was because I didn't know about it. And that's what I meant when I said I wasn't using the right tools, or I didn't know about the right tool. So we got rid of these, and they told me about this IC, which is the MAX 7221. It's a driver for 7-segment displays. It can drive 8-digit 7-segment displays, which is exactly what I needed. So ordered a couple, a few days later, showed up, awesome. And it is connected via SPI as well, and I had to do software SPI because the software for this doesn't let go, and it just got complicated, so it's totally fast enough to run on the software SPI. But it's got a pin for each digit, and then it's got pins for each of the segments. It sends it once when it writes it, and then this IC handles all of the refreshing at the right time. So now it just works perfectly, and I'm super happy. The only weird thing is you can see this is digit 0, 1, 2, 3, 4, 5, 6, and 7. It's reversed from what I have in the software. I think the function is called print digits or write digits, something like that, and it takes 8 digits, and in the software I have 1, 2, 3, 4, 5, 6, 7, 8. For whatever reason, it's backwards here. And I'm not going to change the pins. I could do that. I could just swap them all around so it's right, but I want to keep the pins correct so the schematics are right, and it's less complicated when I build the perf board. I'll have to do some kind of weird stuff in software where I flip the whole thing around so it prints out right, but just software, not a problem. And that's it. The complicated part is going to be getting all of these wires into a perf board that's small enough to fit in the enclosure that I want to build for it. And I keep saying that I want to do a PCB. I thought about it and I kind of planned on doing it for this project, but I'm glad I didn't, because the time frame when I would have ordered that would have been that configuration and it would not have worked. So let's dig into that get a some perf board and get all this stuff on there, and that part I will film because it will be cool.
Do you like winning free stuff? Are you an electronics hobbyist? Do you like building cool projects and winning prizes for what you build? The Element14 Community presents Project 14, the member-driven destination where you decide on the challenge. You enter projects to win monthly prizes and you vote on the winners. What are you waiting for? Join the Element14 community so you too can enter one of our contests or submit an idea for your own. Join now!
Here we are in the CAD design for this project. As usual, I put in all of the electronic parts and then design around that. I've got the TFT screen here, the encoder, the Arduino, and this is kind of an approximation of the proto board for the 7-segment displays, which, as you can tell, I designed these ones because they're not very detailed. When I built the Maker calc a while ago, I really liked the aesthetic of that and the way that the design came out. So I thought I would apply some of those same ideas here. It's similar in a couple of ways, where I've got a little bit of a reveal and a white bottom and a darker top piece, but it's a very different shape. So we'll have to see how that turns out once it's done. Again, I decided to go screwless on this, so there are no screws. Instead, I have some tabs that will hold stuff together. On the bottom piece here, I've got these circular tabs, and on the top, there's a matching hole. I'm hoping that will just kind of click together and hold that in place. To hold the electronics in, I have a series of other tabs that will hold it in, I hope. Let's get rid of these, and I'll show you what they look like. I'm a little worried about it because it might be difficult to get in here and clean these up after it's printed. If that's a problem, then a little bit of hot glue is going to go a long way at the end of this. And you know, they might be brittle. I don't know. I haven't printed these before. I'm hoping that these are static and that I can push the part down and it'll click down underneath this little tab here, but we'll just have to see about that. I think I'm gonna have a lot of 3D printing time ahead of me in the next couple of days, so let's start the 3D printing process and get on to building this thing. This project ended up being extremely code heavy. As you can see, there is a lot of it. If you really want to dig into it and see what's going on, head over to the Element14 community and click on the link for Github. You'll be able to see all of this and look at it all you want. And if you have any questions, feel free to hit me up on the community and I'll do my best to answer. Instead of going through this line by line, which would take way too long, I'm just going to cover some of the user configurable stuff in case you want to build one of these for yourself. In the main sketch, there's only two. There's sync time for NTP and another one called title color, which you will see when we do the demo. Everything else is in these header files Wi-Fi credentials are exactly that, Wi-Fi credentials. And the time zone configuration happens in 2 files. The first one is a configuration for the time zone library. There's one for each hour of the day. I know there are way more time zones than that, but I didn't want to configure every single one of them because it would just be too much. And instead I just decided to make it configurable so you can set it up however you want it. Let's look at my time zone here as an example. You have 2 time change rules, one for daylight savings time and one for standard time. And what it does, it says on the second Sunday of March at 2 a.m., set the offset to -420, which is -7 hours from UTC, which is the daylight savings time setting. And then switch back to standard time on the first Sunday of November at 2 a.m. and set it to -480 seconds, which is -8 hours from UTC. Over in time zone tz_config.h, there's a data structure that has each one of those set up in it and a name. So you can name it whatever you want, and this is the name that will display on the display of the device. I can name this Home instead of Pacific or whatever I wanted, and it'll work just fine. Just don't make it too much longer than that one, which is pushing the upper limit of that string. And then down here we have this time slot structure, which are all the defaults for everything, all the different time displays on the display. This very top one, index 0, is the default, and it should be your local time zone. So whatever your time zone is, grab the index here and pop it in there. This Boolean value is 12-hour or 24-hour. False is 12 and true is 24. When you make changes in the device itself, it changes this data structure. That's it for the code. Let's take a look at the device and see how it works. Here it is, assembled, working, and done, which makes me very happy. Let's take a look at it and go over the features and show you how it works. First thing I would like to point out is the Wi-Fi indicator here. There are 4 levels of indication, which are based on the RSSI value on the radio on the Arduino. There's a date and 8 time slots is what I ended up calling them on this display, and 2 on the 7-segment displays. Each time slot has a title, which we saw in the code, and the hour offset relative to the current time zone and not offset from UTC. So just remember that. These are relative to my time zone, which I thought was a little more informative to me personally. And there's the same information for the 2 7-segment displays. And originally I had seconds attached to each time slot, but it took up too much space and the seconds never really changed between time zones. So I just threw it up here in the corner. And in a fit of needing to write more code for whatever reason, I added this progress bar that kind of scrolls across. Each one of these little blocks is 1 second. And there's a really horrible gradient from green to red as it goes across, which you will see. It's nonlinear, bad math, but it adds some color to the display, and that's what I was really trying to get at. And that's it as far as looking at it. Those are all the features. But what we can do is change any one of these time slots. So I'll show you how that works. Might be a little weird here with the angle since I'm filming, but let's change Tokyo. And this is the menu system here. There's a cursor. As you rotate the rotary encoder, it just kind of cycles through forward and backwards. It's not perfect. It skips every once in a while. I'm not sure why, but it does. So when you want to change something, you push straight down. It'll take you into this menu, and you can select any one of the time zones from the config files that we saw earlier. So let's change this to Moscow time. We can scroll through here. We can even go through backwards. No. That happens because of the weird angle that I'm at. When I push straight down, my thumb kind of rotates it a little bit. Go up. Set and exit, and there you go. Now it's set to Moscow time. We can do that with any of the time slots on the TFT or over here on the 7-segment displays. And now you're going to get to see one of my bugs that I couldn't figure out in time for the demo. But after you go into a menu, and within a minute, I think, is what it is, I get this funny line right here. But then it goes on and works kind of normally. This can easily be fixed by just going in and refreshing it by going into the menu. Let's change this 7-segment display to Pacific time, but we'll do 24-hour format. And there we go. Fix the little bug, and it's now set for Pacific time in 24-hour format. Well, that's it. I'll give you a little bit of a side view here. See how that Maker Calc aesthetic kind of came through. And that's it. It works. Makes me very happy. Well, that's all we have for today. I hit a few snags along the way, but it all worked out to be a good learning opportunity, like driving the 7-segment displays. I knew I needed more I/O, so I went with what I knew, which ended up being wrong. It wasn't until halfway through the project that I learned that there are specific ICs just for driving that type of display. And of course, working with Arduino code is something I'm continually learning, so lots of good practice there. What other information would you have put on this display? And can you think of any features that I may have missed an opportunity on? Let us know on the Element14 community at element14.com/presents. We'll see you next time, and until then, keep making.